Okay, so momentum in two dimensions, or things that are involved two dimensions. In other words, we're talking about situations where instead of, say, a car colliding head on with another car, it's a little more realistic maybe, where a car would collide with another car at some sort of angle. So they might come into each other like this. And how do we handle the fact that momentum is still going to be conserved, but deal with the fact that we have things at angles here and that everything's not in one dimension? Basically, we can't handle the direction by calling one way positive and the other way negative. It's not that simple. We get into situations where we have angles. And so, just like any other situation, we treat them as vectors and we split it up into two parts. We look at the x dimension separately from the y dimension. If we're using reference angles, we use cosine to get x components, sine to get the y components of the various momenta, and then do our business over here with the conservation of momentum, and do our business over here with the conservation of momentum. And then at the end, if we have a final momentum or something along those lines, we then recombine the final momentum components using the same way we've always recombined vectors and added the two components together. Your resultant vector, you recall, is going to be the square root of your x component squared plus your y component squared. And the reference angle will be the inverse tangent of your y component over your x component, just like we learned at the start of the year. So the idea is break everything into all the vectors into their components, deal with this idea that instead of this statement, really instead of, but we're going to look at it as the original x, all the x momenta originally equal all the final x momenta. So the conservation of momentum still holds. We just look at it for x. And then meanwhile, at the same time, or a little bit later on, or during the problem, we will look at the original and final momentum in the y dimension being equal as well. So the conservation of momentum really gets split into two parts during the course of the problem. Now the first problem we're going to look at in a moment, one of the two dimensions, that's completely different. I think the y in the next problem is not conserved and not really an issue because there's an external force involved and all the fun is in the x. So the first problem or two is a couple like that. We're only looking at one dimension anyway, but there are two in the problem, but only one of them is of concern to us. And then we'll look at problems more like, say, this one, where two objects, maybe not even that object, maybe ones that come in like that angle and then one comes in at this angle, something like that, where they both have x and y components and so forth. So let's take a look at how this might look. So we'll use this problem as our example. So initially, all of our momentum in this problem is in the x dimension. Afterwards, there is a little bit of, he has a momentum in two dimensions now because he's jumped off and he's going up and to the right. But the up part, the y component here, I'm not really concerned about because the boy pushes on the skateboard. The skateboard pushes on the boy, but the skateboard interacts with the earth. And we're just going to call that an external force. And so the skateboard's momentum in the y afterwards is not affected because of this external force, since we really can't look at conservation. So the momentum, though, the momentum in the x, however, needs to be conserved. And interestingly enough, it's because of the interaction with the earth, the only momentum left in the x for the skateboard is in the x after the boy jumps off. So what we're going to need to do in this problem, and there's a couple like this. There's one involving, I think, a mine car with a piece of coal falling in it. There's another one where a girl skips a rock off of a boat. There's similar situations. let's figure out the initial momentum in the x, which happens to be all in the x. So initially we have a 47 kilogram kid riding, let's see, this much of a skateboard. So they're all one object. So we're going to look at that total mass at a velocity of this. So the original momentum, which happens to be all in the x, has to equal the final momentum, all in the x. Just worry about the x in this case. So we have the total mass of the boy plus the skateboard times the original velocity. Original. You saw me hit this, right? There you go. Now, afterwards, we have the final momentum of the skateboard, which is all in the x, but we'll look final of the skateboard, plus the final momentum, x momentum, key here, x momentum, of the boy. Okay, so let's run through this. We have 47 and 2.6, so 49 point, I already forgot, 6, right? Kilograms, boy and skateboard, moving at an original velocity of 5.3 meters per second. And we'll call that positive, left to right. Equal to, now mass of the skateboard is 2.6. I don't know the final velocity of the skateboard, but it is all in the x. Plus, now, this is where the component part comes in. I'm only interested in Jimmy's horizontal component to his momentum. So therefore, the horizontal component of his velocity. So the x component of his momentum is going to be his mass of the boy times the x component of his final velocity. So that x component is going to be the 47 kilograms times the, well, let's go to the magnitude first. Speed of, let's see, in the boy's velocity relative to the sidewalk is 6 meters per second. Oops. Times the cosine of 8.9 degrees. Because I'm only interested in this part of it, not how fast he's going upward. See, there was an impulse in the vertical. Because of his external interaction with the earth through the skateboard, he now has added momentum, changed his momentum, but he hasn't changed it in the x. So we have x component of his momentum. Turns out to be, with some quick calculations, I got 278.6 kilogram meters per second. So 278.6 kilogram meters per second. And positive still, going to the right. So the only thing I'm looking for now is the final velocity of that skateboard. So let's see if all this works out. On the left, I have 49.6, their total mass, times 5.3. So I had an original momentum of 262.88 equals 2.6 times the velocity of the skateboard afterwards. Remember, it's all in the x. The skateboard only moves left and right. Plus the 278 268.6. Now notice, if you're looking at it, you're already seeing this going to come out negative, which makes sense because that velocity is going to the left for the skateboard. So 262, so I'm going to minus the 278 from both sides. 278.6, that is. So I have negative 15.72 kilogram meters per second equals the 2.6 kilogram mass of the skateboard times its final velocity. Divide by the 2.6, and the skateboard's final velocity is negative 6.05 meters per second to the left, so hence the negative. And that's all in the x dimension, of course. And yes, looky there. Well, one can still do physics even though he's tired. All right, cool beans.